Yes, and due to the fact that it is only a sketch, it is important that you do the right description of the axis. Somewhere here we start with 0 dB. And our passband attenuation should be smaller than 1 dB, and the minimum stopband attenuation should be larger than 4 dB. So in terms of attenuation, don't forget the minus sign. For example, here, this is equal to 1 minus delta sub pass. And you can sketch, for example, minus 4 dB. And this is equal to delta sub stop. And when we want to correctly draw the passband and the stopband in terms of frequency, then we have to consider our values for omega pass and omega stop. So omega pass was omega, let's say pi somewhere here. Then we have 0.5 pi. Zero 0.4525 pi. Here, and then we can sketch our tolerance scheme. So how do we call this area here? Yes, this is the passband. From 0.24 pi to 0.5 pi, we have the transition band. And of course, our stop band. Okay. And depending on the filter order, what is the slope of our frequency magnitude in the transition band?
The higher the order, sharper.
That's one point, but you can relate to a certain value, the order. Excuse me? Not the width, the slope. So the factor, how strong the magnitude response is decreasing. Could you repeat it louder, please?
Minus.
This is in terms of power, and when we look at just the amplitude, 20 dB. So usually filter order 2, then we have minus 40 dB. Okay. B, calculate the minimum order n as well as the cutoff frequency in such a way that the filter specifications are fulfilled. So first we will start and calculate the filter order. Filter order n. And what we have to consider here is equation 1, and we can build a connection to our values here, to 1 minus delta sub pass and delta stop. And in doing so, what we get is our magnitude response so for the passband is then equal to 1 minus delta pass. And we have to take care of the exponent. So we have the squared magnitude response. And of course, when we do this with the stop band, what we then get is delta sub stop to the power of 2. We can then use equation 1 and replace, not equation 1, equation 3, and we replace then h of j omega pass and h of j omega stop with our expressions here. And what we get is a long formula. So I think you do not have to write that down. I will provide you the solution. You can just write then down the filter order. Just take a look at my writing here. So replace h of j omega pass and h of j omega stop by So in general, this is nothing new. We already performed this calculation in the last exercise, which is repeated here. And when we calculate these values, when we say 1 minus delta pass is equal to minus 1 dB, how can we convert the value in dB into a linear value? Who started? But don't forget the minus sign. So it's 10 to the power of minus 1 dB divided by 20 dB. So plug in here 1 equation, and what we get is 0.899. And when we perform the same calculation for delta stop, which was equal to -4 dB, then we get 0.631 as a linear value. Okay. So what is still missing? Our omega subpass and omega stop. And there was a non-linear relationship between the analog frequency and our digital frequency here. So this is the digital frequency. Last exercise, you did the sketching via the tangents. Does anybody has the formula in his mind? Otherwise, I will write it down here. Okay, yeah, write it down. So omega in general, digital frequency 2/t times tangents of omega divided by 2. So for t equal to 2, and then we can calculate our omega pass. By 2. And don't forget, when you calculate these values, that you use radians in your calculator. Keep that in mind. I write it down here. Okay, this gives us 0.3959. Equal to 1. Oh, sorry. Should we stop here? Just to note again what we did, we built a nonlinear relationship between the analog frequency and the digital frequency. And this process is called frequency warping. So now we did the calculation for our unknown values, and then as a final step, we can calculate the filter order n. We have to plug in all these values in our formula. And so we choose n equal to 1. Yes, question, please.
Can you go back to the sketch?
To the sketch.
Yes. The big omega of omega.
Sorry, this is, yeah, you're right. So we have our analog frequencies here. Yeah, thank you. Good. So we finished our first task to calculate the filter order. Now we can move on and calculate our cutoff frequency. And at the beginning of our exercise, it was mentioned, in addition, we would like to make sure that the maximum passband attenuation is met exactly. So please be careful if we ask for the passband or the stopband as a matching parameter. So in terms of the passband, we get for the cutoff frequency let's say take equation 1 into account again. What we have here, 1 minus delta sub S squared is equal to 1 over 1 plus omega pass divided by omega c so passband this is the important point here in this context. Good. When we then rewrite our formula and solve for omega c, what we then get is 1 over 1 minus delta sub S equal to 1 plus omega plus omega c to the power of 2 times n. We can then plug in our values and solve for omega c, and what we get is this. And this gives us 0.7782. Yes.
So there's as fractions that because as I see it, you can just the 1 divided by 1 divided by.
Yeah.
Or is a fraction somewhere else? I can't see it.
Let me check that. So what we do is, yeah, you're right. Thanks for that. So what we do is 1 divided by 1 minus 1. Then we take the 2nth root and divide omega sub pairs with this expression. Yeah. Thank you. Okay. So we finished task B. We calculated the filter order as well as the cutoff frequency. And then we can move on with task C. Where we should determine the digital filter system functions or the transfer function. Again, we use the bilinear transform. Calculation is done as in the previous exercise. So first we started our Laplacian expression, calculate the poles. Consider only the poles on the left-hand side in our S-plane, so the stable poles. And then we apply the bilinear transform. And calculate our system function. So as I said, we start with equation 2. Calculate the poles. How do we calculate these poles when you see this expression here? Set, what do we have to? Denominator, exactly. So we say 0 is equal to 1 plus S divided by J omega C to the power of 2 times N. We can solve this equation for S to calculate our poles. And we get J omega c times the 2 times n root of -1. And last time we did some calculations and expressed a few variables here in this equation with other expressions, or with expressions that stay for the same relationship. So first relationship was that we expressed -1 as an exponential function, so it's e to the power of j pi plus 2 pi k. So is that clear for everyone? How do we get from -1 to this expression here? Unit circle, yes. So just keep in mind, we have our unit circle, we have our imaginary axis, our real axis. Here is 1, here is -1, j and minus j. And when we start rotating our rotation phasor, and we start here at -1, then we have the e to the power of j pi, and we can repeat it periodically. So every 2 pi times k, we get exactly at the same point. And this is how we can come to this expression here. And the second part was very similar. We said j.
But sorry,
Yeah.
said that you need the unit circle because you multiply again with a complex number, because j omega c is also a complex number.
So we're here in the z-plane, right?
Yeah.
And when you remember was it the exercise to the C-transform, where we had the relationship between angle, frequency within this z-plane. Okay.
Speaking just mathematically, you need the unit circle because if you multiply with the complex number, the radius will increase. But
No, the radius is defined with the constant. For example, when we multiply it with 2, then we have a circle with radius 2. Here we just multiply with 1. We just leave the 1 away, say, and we have a circle with radius 1. Okay? So the constant factor, which we use as a scalar for the e to the j pi, gives our radius. Good. So same approximation, or not approximation, the same expression. So j is then equal to e to the j pi over 2. Okay. And when we then plug these values in our equation, let's say this one, then we get sk, because it depends on our factor k here, which is equal to omega z e to the j 2 pi to n plus pi over 2. And for k equal to 0 to 2 times n minus 1, we then get our solution for the poles. As mentioned in the previous exercise, the poles are uniformly distributed in the complex S-plane.
So you just make a you distinguish between n to the odd and even, right? Because worst case would be that minus 1 is high, and otherwise it's just minus 1.
Again, the traffic was loud.
You distinguish between odd numbers and equal numbers. In equation 1.
Okay, because
You distinguish for odd ends, odd values of n, and even values of n.
yes, so but we always multiply our n with a factor of 2, so we always get an even number. Okay, so where are we? Around the circle with radius omega c. And then we can insert our n filter order, n equal to 1 and k equal to 0 and 1. And this gives us 2 poles. So as 0 for k equal to 0, we get minus omega c, and for S1, we get omega c. Okay, then we use the identity as it was performed last time. We could say h of c of s s to the power of 2 can be separated in hc of s times hc of minus s, so in a stable and an unstable part. And we consider the stable poles. And what we then get is omega c divided by s plus omega c times, so usually we would have here the minus omega c, but we directly calculate it and say this is then equal to omega c minus s, and we leave the minus sign. So, and then again, we only consider stable pole. So this is the stable part. And what we then get is HCS is equal to omega c divided by s plus omega c. We can insert, plug in our cutoff frequency. And then we are finished in the S domain. And then we have to apply the bilinear transform. And we said the transformation equation was S is equal to 2 over T times 1 minus Z to the power of minus 1 divided by 1 plus Z to the power of minus 1. Again, T was equal to 2. And when we insert S in this equation here, we then get h of z is equal to omega c divided by 1 minus z. Z minus 1 plus omega c. So this is the equation that we can use in our Z domain. So in the digital world. And as a last question, it was asked to calculate the filter coefficients BK and AK. And there we have to go a little bit backwards in time when we started with our Z transformation, and in general, our system transfer function. Well, let's say first calculate coefficients. BK and AK. We have to go back to our standardized form of our system function, and h of z is in general the sum of k from 0 to large N times bk times z to the power of minus k divided by 1 plus the sum from k equals to 1 to large M times ak times c of the power to the power of minus k. This was the Z-transform equation in general form. And we now have to rearrange this equation that we get a similar expression to this one here. This is some mathematical calculation. We have to perform some rewriting, and let's say rewrite this equation here. And in doing so, what we get again, I'll write it down. C divided by 1 minus C plus omega C. First, we multiply our equation with 1 plus C minus 1 divided by 1 plus C minus 1 to get rid of this expression here. And we then come to this form. We can then do the multiplication and we get omega C plus omega C times Z to the power of minus 1 divided by 1 minus Z to the power of minus 1 plus omega C plus omega C times Z to the power of minus 1. And then we have to perform one final step. To make it clear, I perform another step in between. So then probably someone sees the similarity, and then we can define our coefficients. So I know there is much calculation to do, but just one example for you that you see how we can calculate the coefficients of such a filter kernel. And usually you don't do this by hand, but just for everybody who's interested, one time we do it, but usually when you do your filter design, you use MATLAB or other programs. But just to show you the whole thing of a filter design and how you can do it by hand if you're motivated. But I think there won't be many students who will perform this by hand, this calculation. And as a final step, I will just quickly insert how we can rewrite our standardized system function so that we can do a coefficient comparison. So we have h of c is equal to b0 plus b1 times z to the power of -1 divided by 1 plus a1 times z to the power of -1. And now we have to bring this equation in a similar form to our standardized form, and then we can compare the coefficients and finally calculate them. So quite an awful thing to do it by hand. So for example, when you take a look at this one here, we have to do a calculation that we get a 1 here as well. And what we do is to divide the whole equation or multiply it with multiplication with and what we then get is omega c divided by 1 plus omega c plus So now we can compare our coefficients. We have a b0 which can be expressed via this term. We have a b1 which is equal to this term, and an a1 this term. And what we finally get, b1 is equal to b0 is equal to b1 equal to 0.4376, and a1 is equal to minus 0.1247. So not an easy task. It consumes really much time, and as I mentioned before, nobody wants to do it by hand, but for you, that you just see it and perform this once in the exercise. We did it here for completeness. And finally, I want to conclude the IIR filter design process just in words, and to summarize the steps that we performed. So what did we first do when we started our filter design?
Figure out the frequencies and the magnitudes during the run.
And in which world? I would say in the analog world, right?
I think, yeah.
Okay, so let's write that down. Determine desired frequency response in terms of analog frequencies. And when we do this, then we can derive our tolerance scheme. And as a next step, we did the conversion from the analog frequencies into the digital frequencies. This is step 2. So we convert the desired frequencies into digital frequencies. Then as a third step, we mapped those digital frequencies into analog frequencies. So the frequency wrapping process with our tangents formula. We then designed the analog filter in the S-plane, where we get rid of our unstable poles. And then to be able to work with this filter in the digital world, we then performed our bilinear transform to map it in the Z domain. And if we then do this further, as I showed you today with the calculation of the coefficients, then we can use these coefficients in MATLAB, for example, and yeah, do the filtering. So 5. So in general, these are the 5 basic steps that we have to perform to get our digital filter in terms of our, or with reference of our analog filter. And this is the whole process of designing an IIR filter. Now to our second part of this exercise, correlation. Have you ever performed a correlation of measurement data? Or what was the goal when you do a correlation of measurement data? Similarity? Yes, that's one point. And this is what I wrote down there. Signal processing, correlation resembles a measure of the similarity of two signals, and in which technical parts it is interesting to find out these similarities. This is the thing that we will talk about now.
When I was a student, I used to use a lot of that. Who always correlates some random noise with the filter out the noise. So it's just like a decent filter. It was combined with the low pass filter, you measure on locking frequency. That's why it's not locking.
Yeah, so this is a device, a certain device that performs the correlation, and in this exercise we will do it in the digital world, so with data processing, but that's, for example, a device which you can use to do some correlation. That's correct. And here I mentioned the formulas. We have to distinguish between two types of correlation, the autocorrelation, and later on here, the cross-correlation. Both are similar, and cross-correlation is used when you want to find out the similarity between two different signals, and autocorrelation is performed when you want to find out the similarity of a single signal, signal itself. For example, to find out the periodicity of a signal. And what would you say when you get when you perform the autocorrelation and you get the result like this one here? Would you say that the signal is periodic or not? So first guess.
I guess yes.
Because the autocorrelating or the autocorrelated section is periodic, yeah, exactly. And for example, there might be some values which are slightly lower. So for example, when you take a look at this one here, but this could always happen because of some round of errors, bit errors, and so on. So just an example in this case. And yeah, then the cross correlation. So when you perform the cross correlation, you can perform it on two different ways. You can shift one signal through the other or vice versa. So that doesn't matter. You just get different coefficients with a different sign. This is expressed here in this formula. And one example for cross correlation here, when we want to determine signal delays, for example, when you think at your car and you try to park in a city in a parking spot, usually every car has a parking sensor system which gives you a hint how close or how far are you to the other car. And there you usually, or these parking systems use pulses, but the best thing would be to apply a noise signal. And as you can see here, we have two different noise signals, white noise. When we cross correlate both, then we get a single peak at a certain time delay tau1, when these signals are most similar to each other. And by calculating this time delay, and of course, when we know the speed of sound, we then can conclude to the distance. And this is how it is usually performed. Just to give you a comparison to the linear convolution, which is quite similar. But the important thing is here that we do a mirroring of our signal, which is not performed when you do the cross correlation or the autocorrelation. So that's the most important difference between convolution and correlation. And you think about the linear convolution of two signals. I just sketched the blue one and the yellow one. What we get as a result is the green one. And the length of our convoluted signal is then usually the length of both sequences added minus 1. So when we have here a length L, and we have here length K, then we can say the final sequence or the resulting sequence has length L plus K minus 1. And so far we always perform the linear convolution, but there is another convolution as well. This is called the circular convolution, which is applied for periodic sequences. And imagine you want to convolve two signals and one is just a periodic signal. Then it is enough to do the convolution within a certain period, and this period is then signed with a large N here. So otherwise you would never stop convoluting the signal. You would just keep on calculating, and the end result, the final result y of n, just is a periodic sequence. Okay. So first we will start with the autocorrelation. We have a given signal here, this triangle-shaped signal with these values here. On our x-axis we have the time in seconds, or just our sample values n. And we should calculate or determine then the frequency of the given signal via the autocorrelation. And there's a certain scheme that we can use when we want to calculate the autocorrelation function. And the simplest way is to write down your signal in a short table. So we start with our signal values 0, 1, 2, 1, 0, 1, 2, 1, and 0. And we have to perform our autocorrelation m times. So this is 1, 0, 1, 2, 3, 4, 5, 6, 7, and 8. And we can then start with the autocorrelation. And what we do is we just rewrite our signal values again. For m, the signal for m equals to 0, the signal is not shifted yet. So this is the first calculation that we do. And when we perform our multiplication and summation of these values, so what we actually do is 0 times 0 plus 1 times 1 plus 2 times 2 plus 1 times 1, and so on. And as a resulting value, we get 12. Then we shift our signal, one sample to the right, rewrite it again, do the calculation, and we get 8. And so on and so far. We just perform this shifting until the whole signal was convoluted once with our starting signal sequence.
In the row number 1, just consider that the first column is 0 then, where there's no number.
So this was our signal sequence, wasn't it? Yes, we started with 0.
No,
Yeah.
but I mean, in the row number 1, you shift the signal to the right? So there's nothing in the 0 column. It's okay, but should I consider that it's just 0? This doesn't exist, so I don't count that into my calculation.
It is counted in your calculation. So you start with the signal. Both are 100% overlapping.
Yeah.
Then you perform the first calculation.
I mean, you get the sum of the volume 1. So there's no, so just 0 times
So
1
it's
is
0. Here, so here we get 0. Here we get also 0. This is 0. So first, it's always 0 when we multiply with 0, right?
Yeah, but that's not what I mean. I mean, line 1,
Line 1, yes, here.
column 0. There's no number there.
No, there is no number here.
Okay, so this does not count in the sum of the line number 1. That's what I.
No, no,
Okay.
it's not counting, right? So these gaps here are empty. These cells, okay? No. So these are empty, okay? So not a complicated calculation. And when we perform the calculation for every shifting step, we get these values here. And I then just sketched it here in this small plot. What we have here is 12. We got a 6. And as you can see, there is another maximum occurring at a certain distance. In this case, the next maximum was here, our 6. So this is 4 shifting steps away. In MATLAB, these shifting steps are called legs. And when we have our leg and we know that we sampled each sample once per second, we can then calculate our frequency, which is then 1/4 hertz. So this is our signal frequency. We can then move on to question 2. Okay, so we have here our values. This is 12, Next is 8. Then we get 3, 4. Wrong, sorry. Um, This is 3, not 3. Oh, well, here is the 4, 3, 4, 6, and always the next occurring maximum within the autocorrelation indicates the periodicity of a signal, okay? So this is why we consider this maximum here as the next one. And this indicates our period of the signal. Okay, then question 2. We have 2 sound signals, one that is transmitted, it's here on the left-hand side, and one y of n, which is received by a receiver. And we now want to calculate the distance between the sound source and the reflecting object. What do? We perform a cross, yeah?
Like, won't you multiply with the signal before, like the
What do you mean?
like when you, I don't understand like how the last go like.
When you break, it's it will stop and the other one is moving. So that's means that put in the table and stop.
Exactly. So you correlate the signal with itself.
Yeah, okay.
Just start rewriting both, and then start shifting one version of itself, okay? So, yes, now we perform the autocorrelation, and here in question 2, we use the cross correlation to determine the distance from a transmitter to a reflecting object. Transmitting signal x of n, receiving signal y of n. And again, we can write down our values. So we start here with our received signal. And then we have to perform, so let's just imagine we start here at this point. This is our sketch it here. So when we say for example 10 here, so it's not correctly scaled, but the amplitude doesn't matter. So when you want to perform a cross correlation of 2 signals, you do not have to normalize their amplitudes. For example, with our, when we just sketch our transmitted signal into the received part, what we then get looks something like this. Oh crap. Samples. only have 8 samples, so this is here, there, there, this one. So this is the process when we start. We shift our yellow signal, the transmitted, in this direction through our receiving signal. And of course, we can first shift it 1 step, 2, and then they start to overlap when we shifted it 3 times. And this is why we can start here with m equal to 3, and then perform the cross correlation. So first, we then write down our values. So here we have our 0. This is the first signal value. We then get our -8, -10, -8, 0, and so on. So shifted it 3 times, and we get the 0, which of course results in a 0. Shifted 1 step further to the right, we get 0 again, -10, -8, and 0. Perform the calculation. Four, 5, it should be 4. Did I write down there? 4, 5, 4, yes. Of course. Sine wave. Okay. So you keep on shifting 1 signal to the right and calculate the cross correlation. And so on and so far. I think you're familiar how it works. I will just write down the values here and upload the whole solution. So in general, it's not a complicated calculation. And the value that is important for us, that shows us our time delay, is the maximum value, because when both signals are overlapping for 100%, then we get our max for the cross correlation. And at this time step or shifting step, we then can calculate our delay. So this is this one here, 228. And we did the time shift 11 times. So our max And we can then calculate the distance. The time difference in samples is equal to 11. Our formula when we want to calculate the distance via to an object, time times velocity. Here we have to keep in mind that we have a reflecting object, so the echo, or let's say the transmitted signal travels to the echo and backwards, so we have to divide it by 2. And what we get is then our sampling frequency considered is 1/10,000 samples, seconds per sample. So this is the time when every single sample is taken, times our shift, 11 samples, times our velocity, divided by 2. This gives us 0.825 meters. So, question 3. This refers to a linear convolution. We have a noisy signal and you want to smooth the signal by using a moving average filter. So when you want to smooth a noisy signal, you usually apply a low-pass filter to get rid of the high frequency noise signal. We use a moving average filter of 3rd order. And when we know the filter order, then we can directly tell something about the filter length. So 3rd order means which exactly 4. We have a filter length of 4. And one property of our moving average filter is when we take a closer look at the impulse response, that every coefficient has the same value. So it's smoothing filter. So in this case, when we draw the impulse response of our filter, we have 4 coefficients, filter length equal to 4, and each coefficient has the height 1/k. So imagine when you want to perform an averaging, for example, a sequence 2, 5, 6, and 3. What you usually is you add all these values and divide it by the total number. And you could rewrite this in terms of 1/4 times 2 plus 1/4 times 5 plus 1/4 times 6 and so on. And this is the same thing that a moving average filter is doing. So when we perform a moving average filtering and we do the convolution, the linear convolution, then we multiply each signal of our input with the filter coefficient of the moving average filter, which is equal to calculating an average of the whole sequence. And this finally results in a smoothing. So just a short summary of the linear convolution. We first plot both signals, our impulse response and our signal that we want to smooth in our I domain, I say, with the index I. We mirror impulse response, shift the impulse response, then afterwards n positions to the right. So we have to shift this sequence here totally to the right until we are through our signal. We can also do this using a table. We have here our input signal, and when we start with our shifted and mirrored version of the impulse response of our moving average filter, we have the filter coefficients 0.25, 0.25, and 0.25. We can calculate it for y of 0. We get 0.25. Then perform the shift. Calculate it again. And so on. And when we use the table, it's not that complicated to do these kind of calculations. So I will write down the results. And finally, we then get a smooth version of our input signal when we use a moving average filter. You can try that with MATLAB, for example, at home. Build two vectors, two sequences, and compare the input signal and the filtered signal, and then you will see that there is less noise in the filtered signal. And last exercise, question 4. We do a circular convolution. Circular convolution is done when a sequence is repeated periodically. And when we write that down here in this content, we can do this. So write down our mirrored version. So this is our mirrored version of h of n. Because Oh, what did I do there? Because it's repeating periodically, okay? So when we start, let me see, how can I write that down here? We have our input sequence 1, 2, 3, 2, 3, and 4. We have our impulse response h of n, shifted and mirror it. So what we usually get is 1, -1, 2, -2, 1, and 0. And due to the fact that it's repeating periodically, so it starts again, we then have our 0 again here, 0, 1, -2, 2, and so on. I didn't write it down. Okay.
The zero, I can put the first and put the 1. Yeah, I get it.
You got it. So this sequence is periodic. Okay. And then we can put all these periodic sequences together and shift it through. How should I write it down to make it clear? Mirrored and periodic version of h of n. Is that okay for you guys? Mirrored. Version of h of n. Okay. So I think the most complicated part here when you perform a circular convolution is to write it down correct in a table, to not be confused when it comes to the periodic sequence. But then the calculation in general stays the same. And 0. And we should perform it 6 times. N, large N is equal to 6. In total, we got 6 steps here. And then we can calculate values. Okay. So we can summarize that the convolution, it doesn't matter if it is the circular convolution or the linear convolution, is quite similar to correlation. Both are related to somehow a convolution process, but the correlating functions are not mirrored. And that's the main difference between the correlation and convolution process. When you have to perform a correlation or convolution, use a table, write it down, and then I think it's quickly done. And that's so far to our exercise signal processing. Have you questions so far? So feel free. I recommend you to use in Ilias, the forum, ask your student colleagues. Maybe they can answer some questions as well. I think it's some kind of a practicing effect if everybody uses the forum first before you ask us in an email. Feel free to do so. But maybe these questions are interesting for your colleagues as well. We will then write you an email with a certain, I think it's in September, when we, so when we have the question time, please prepare some questions, write these down in the forum. We can then prepare ourselves for these questions, and I think we'll write you an email when we want to. Yes, please. The cheat sheet, when the cheat sheet is ready, as soon as possible.
Probably this week if we want to practice that.
Mm-hmm. Yeah. Yeah, we want to provide you the cheat sheet as fast as possible. Of course, that you can practice using the cheat sheet.
Maybe this week, at least next week.
Okay, so
Is it content?
we are almost done with the cheat sheet, so probably this week, latest date is next week then. And yeah, prepare your questions, please. Ask them first in the forum in Ilias, so that we can prepare ourselves. And yeah, that's so far. So have a nice day and good luck for the examination.